This will be the review video for the Unit 2 study guide. So these are questions and topics that you'll need to be prepared to answer questions about on the Unit 2 test. So in the first one, the first few questions are about classifying and organizing, categorizing matter into different groupings: physical, chemical changes, elements, compounds, and mixtures, which we've gone over in the last couple of weeks. So the first one is talking about, are these chemical or physical changes? So we have boiling water to make syrup, and really it's the boiling water part that makes sense, or that you have to refer to. Boiling, melting, freezing, those are all physical changes because the water goes from being liquid water to being steam. That doesn't change it into some other substance. Bending an iron bar, anytime you're changing the appearance of something without changing its composition, that's a physical change. So bending or even breaking something into two pieces is physical because you're just changing its appearance without changing the substance of the material itself. Statue of Liberty slowly turning green, that is the result of oxidation, which is a chemical process. It's essentially rusting, and it just has to do with the fact that the material there is copper. That's what gives it that green tone. Hand sanitizer evaporates. Evaporation is a similar process to boiling. It's just a change from liquid to gas state. Mixing flour and sugar in a bowl. Mixing, right? Mixtures are physical combinations of substances. So just putting the flour and sugar in a bowl and mixing them together doesn't change anything about the flour or the sugar. It just mixes the particles of sugar and flour into more of a uniform mixture, but it doesn't change either substance directly. A candle burning. Burning is always going to be an example of chemical change. That's combustion, which is actually the same process as the rusting or tarnishing of the Statue of Liberty. It has to do with combining with oxygen. Scented wax melting in a warming dish. Melting, just like boiling, freezing, or condensing, is a change in state, but it's not a change in content or composition, so that's physical. Crumpling up a sheet of paper, again, just changing the physical appearance does not change the composition. Decomposing. Decomposing is actually a specific type of chemical reaction. So anytime you see a word like that, it indicates a chemical change. What do we have over here? Rust. Again, rust is like the Statue of Liberty tarnishing. It's the same process. We have the candle wax melting, crumpling, cracking, right? Breaking glass is just physically breaking the big piece of glass into smaller pieces. So that's physical. Bubbles escaping. Now this is different. Remember, I said that bubbles or gas being produced is a sign of a chemical reaction, but you have to keep in mind that the bubbles in the soda were already there, right? The carbon dioxide gas was added to the soda and then pressurized to keep it all together. And what happens when you open it is you release that pressure and the bubbles come out. So the gas was already there. It was just dissolved in the liquid until you release that pressure. So those are not bubbles that were created by a chemical reaction. They're bubbles that were there dissolved in the water, or the sugared water essentially, and then they're allowed to escape. A pumpkin rotting, that is another form of decomposition. Let's see, is there another? Oh, that's the last tab there. So none of these, oh, baking a cake. Sorry, I knew there was one I was missing. Baking a cake. So mixing the flour and sugar, just mixing them together doesn't change the composition, but once you start baking, you're initiating chemical reactions and chemical processes that change the composition of the flour and the sugar and the other ingredients into other compounds. And then this one might have been worded better, but because I said mixing flour and sugar doesn't change the composition. Mixing baking soda and vinegar, the actual act of mixing them isn't physical, but what happens when you mix those two things together is there is a chemical change that's initiated. So the combination of baking soda and vinegar creates a chemical change, and that's where the bubbles come from. Again, unlike the bubbles in the soda, which were already there. The bubbles when you mix baking soda and vinegar are the result of that chemical reaction. Okay, classifying things as elements, compounds, or mixtures. On the next slide. These are images from a worksheet that we did recently. And you have to remember that elements are made of one type of atom. Compounds are two or more elements bonded together, which in the case of these drawings means they're actually touching. And mixtures contain two or more different types of substances. So the fact that this is R and SQ, so the circles and the squares touching each other, means it's a compound because it's made of two different elements. This is all triangles, so that's an element. This is triangles, and this is a combination of the first two. Right? So we have the molecules of round and square and the atoms of triangle, so that's a mixture of those things. Here's an example of an element. This is an example of an element that's made of molecules. So you can have molecules that are elements and molecules that are compounds. The key is these are molecules, but the molecules themselves are all made of the same type of atom. So there's no atoms in there other than the squares. That makes it an element. Here's molecules of squares and molecules of round. So those go into the mixture. These are molecules of squares and rounds. They're all the same. The same composition means it's a compound. Here we have squares, rounds, and triangles. But again, there are molecules of all the same composition, which makes that a compound. And here we have square triangles and square round threes. So those are mixtures of two different compounds. All right, so now we have to decide if these are elements, compounds on the one hand, which are pure substances, or heterogeneous or homogeneous mixtures. So let's take a look. We've got muddy water. So the water is a compound. Mud is a combination of different types of substances, but muddy water is a mixture. Okay, so it's definitely going to go over here. Now, is it heterogeneous or homogeneous? Well, the fact is when you have muddy water, the mud is not necessarily uniformly distributed. You could make an argument that there might be times when the mud, like during a flooding situation or heavy rain, where the mud is pretty well churned up and evenly distributed. But if you leave the water alone, the mud will settle down. Okay, that's one way of telling whether or not you have a heterogeneous or homogeneous mixture. The heterogeneous mixture will kind of separate if you leave it alone. So like salad dressing is another example. If you shake up the salad dressing, yeah, you can mix everything together. But if you let it sit, it separates into the different components of the mixture, more or less. Sugar is a compound. Gold is an element. It's on the periodic table, so is carbon. Hydrochloric acid is an example of a compound. A Gatorade drink is a solution of pretty much sugar. So it's dissolved in the liquid. It's homogeneous because you can't tell where one part leaves off and the next part begins, and it doesn't separate if you leave it alone. Again, like I mentioned with the muddy water, that's one way to tell whether it's heterogeneous or homogeneous. Silicon dioxide, so you've got two elements, silicon and oxygen. That makes it a compound. Water, we know that's a compound, H2O. Magnesium, that's on the periodic table, so that's an element. Vinegar is actually a solution, right? It's mostly water, but it has something called acetic acid dissolved in it. So it's a mixture, but it's homogeneous because it's very uniformly distributed. Neon gas, the fact that it's a gas doesn't really matter. It's just that neon is an element that's a gas at room temperature. Again, neon, if it's on the periodic table, put it in elements, don't even have to think twice about it. Black coffee, again, that's a solution. Salad is heterogeneous because it's easy to pick apart. The parts are distinct and not uniformly distributed. And I've used the example here, soil is heterogeneous because it's not uniform unless it's been processed thoroughly to make it very uniform. But even then, I would argue that a lot of that is heterogeneous. Okay, So again, this is there's the link down here to the video on atomic theory. You want to make sure you understand the contributions of Democritus, Dalton, Thomson, and Rutherford. And there are some other names. I think Lavoisier is mentioned in the video. That's a very important person as well. Okay, so just be familiar with each person on that list, what they did, what their contribution was to the theory. Did they create a model of the atom? Did they do a key experiment in the development of our atomic theory? And if there was an experiment, what was the experiment about and what did it discover? What happened? And if they came up with a model, what was the model that they came up with? So I won't ask you about all 5 of those, but I could ask you about any of them. In a question, you'd need to be short answer style, be able to explain what those people did and know what they did. So even if I don't tell you, who did it, you need to know who did which experiment. So if I mention the experiment, you need to be able to tell me that it was Dalton or Thomson or Rutherford who did it, and what was the discovery that they made. Okay, here's an example of a question where the student gives an answer that makes sense on some level, but is incorrect. So they say that nickel and copper are isotopes because they have different masses. And helium and hydrogen are ions because they have different numbers of electrons. So the key thing here, the thing that they got right, is that yes, isotopes have different masses. But what they got wrong is that just having different masses doesn't make something an isotope. The first factor that has to be true is that the atoms have to be of the same element. Okay, so if you had nickel, 2 atoms of nickel, for example, one of them has a mass of, I'm going to pick a number at random here, 45, and then you had another atom of nickel that has a mass of 46. Okay, those are isotopes because they're both nickel, but they have different masses. So again, they got the second part right. Different masses is key to making something an isotope. But in order for 2 atoms to be isotopes of each other, they have to be the same element to begin with. So the fact that nickel and copper have different masses is because they're different elements, not because they're different isotopes. And they made essentially the same mistake in the second one. Yes, different numbers of electrons is what makes something an ion, but it's not the only thing. The first thing that has to be true is they have to be the same element. So hydrogen atoms with different numbers of electrons are ions of each other. So you can have H and H plus, right? If we make this hydrogen instead of helium. So this is a hydrogen atom that has 1 electron. This is a hydrogen atom that has 0 electrons. That's why it's a positive 1, because it's lost one of its electrons. Okay, so you need to understand the key difference there. Isotopes are atoms of the same element with different masses. It has to do with their neutrons. So the difference in isotopes is neutrons. Difference in ions is electrons, but it's not just electrons. They have to be atoms of the same element with different numbers of electrons. All right, so here's a calculation question for average atomic mass. Average atomic mass is always found by taking the mass, and when the isotope is written this way, see how these are all lead, right? They're isotopes because they're all lead atoms. It's just that they're lead atoms that have different masses. Going back to the last question. So to find the average atomic mass, you take the mass. When they're written like this, the number following the name is the mass of that isotope. Then you multiply it times its percent abundance. Okay, so in this case we have 285.6 for 4,000 964.6. Make that a little bit cleaner there. 4,574.7 and 10,899.2. I add all these up, I get 1, 4, 2, 7, 0, 2, and then I divide by 100 because these are all multiplied by their straight percentages with no correction. So I divide by 100, and I would get the average atomic mass of 207.241, and on the periodic table, it's written as, I believe, 207.2. Technically, though, I would round, since these all had 3 digits, I would round it to 207 for the proper sig figs. But again, if you gave me any one of those answers, I'd be pretty happy about that. Don't worry too much. If you get an answer here, you've done all the math out, you get an answer that's not exactly what shows up on the periodic table. Because maybe the percentages were rounded differently, maybe the mass numbers were rounded a little differently. As long as you've shown me the work and you've done the steps correctly, I'm not even looking at the periodic table. I'm looking at what the calculation gives you. So if, let's say you got this and the periodic table said like 206.9, don't think you got it wrong because your answer doesn't match the periodic table. That's okay. All right, so to fill in this table, we can look at the periodic table for some of the ones that we might need, but we don't need them for all of them. Anytime you have the atomic number, first of all, you also know the number of protons, which would be, for example, here 26, and the number of electrons, assuming none of these have a charge, which none of them do in the cases that we see here. So H2, H is the element hydrogen, which is atomic number 1, which has 1 proton and 1 electron. The fact that it says H2, remember that number after the symbol or after the name is the mass. So I can use that. The mass is the number of protons plus the number of neutrons. So that's 1, and it's hydrogen. Okay, so I'm just going to fill the rest of these in as we go. All right, so the only other thing to look out for would be if any of these symbols had a positive or negative sign next to it, that would mean that the number of electrons is different from the number of protons. So if it's a negative, then the electrons are more than the protons. If it's a positive, the electrons are less. So just be aware of that if you're trying to figure out the subatomic particles. The charges affects the number of electrons. All right. So percent composition, okay, what is the percent composition of aluminum in aluminum chloride? So when we're looking at this, in this case, we're only asking about what percentage of the compound is aluminum. So the first thing we need to do is look at the periodic table and say, okay, we have aluminum and we have chlorine. So 26.98 and 35.45. The catch here is that the chlorine is 3 times. So we're going to add that in 3 times, or you could multiply the 35 times 3, but just to kind of show you where this is coming from. If I add all that together, I get a total of 133.33 grams per mole. Okay, so that's the mass of the compound. That's the total. That is the denominator, the bottom half of the equation. The top, in this case, is the amount of aluminum in that compound, which in this case, there's only 1. So it's just the mass of aluminum, which is 26.98. And then I'm going to multiply that by 100. And I end up with 20.24%. Now, if I said, what's the percent composition of the whole compound? Well, then I would do the same thing. I would repeat the total on the bottom would be the same, but the top number would be the amount of chlorine, which I would add those three together. The other trick to that is, since there's only two things in the compound, and I know it has to add up to 100%, I would know right away that the amount or the percentage that's chlorine would be the 79.66%, or sorry, 76%. I would just subtract the first number from 100. Since there's only two, they both have to add up to 100. All right, what's the percent composition of chlorine in barium chloride? So again, going to the periodic table, we already have the chlorine. And then the other part of this compound is barium, so that's a heavier element. So 137.33. So 137.33. And then chlorine here, there's two of them. So just like we did up above, I'm going to add that twice this time instead of 3 times, because it's Cl2, not Cl3 in this compound. Okay, I add all that together, I get 208.53. That's the denominator. The numerator, the top part, what part of that 208 is the chlorine? Well, in this case, the chlorine appears twice because it's Cl2. So I can't just put 35.45 up there. That would only be one chlorine. I have to put it twice. So if I add those two together, I get 70.90. Then I'm going to divide that, multiply by 100, and I get 34.00%. That's the chlorine. If I wanted to know what the barium was, that's the rest of it. So in this case, that would be 66% barium. There's only two elements. They have to add up to 100%. So it makes that second step much easier. I could go through the calculation. I could do 137 divided by 208. It would come out to 66%. All right, molarity question here. What's the molarity of an aqueous solution containing 40 grams of glucose in 1.5 liters of solution? So remember, molarity is moles per liter. They gave me liters, so I've got the denominator. I've got 1.5 liters on the bottom. I don't have the top, though, because they gave me grams instead of moles. So I have to convert the grams to moles first. Periodic table, I'm going to have carbon, oxygen, and hydrogen. C6, so there's 6 of these. C6, H6, or sorry, H12, O6. So carbon times 6, oxygen times 6, hydrogen times 12. And that is times 6 plus 12 being the carbon, plus 1 times 12, so that's the hydrogen times 12, plus 16, which is the mass of oxygen, times 6. That equals 180 grams. So to find the moles, you take the mass that they gave you, divided by the molar mass, and I get 0.22 moles of glucose. So 40 grams of glucose is 0.22 moles. Now I've got moles. That goes on the top. 2 moles. And that equals 0.15 molar. There's the molarity of that solution. Here's a dilution problem. Dilution is starting molarity times starting volume equals final molarity times final volume. So if I start with a 3.5 molar solution, 20 milliliters of it, and I dilute that to 100 milliliters, the question is, what's the final molarity? So I would do 3.5 times 20 divided by 100 equals M2. And when I do that math, I get 0.7 molarity, molar solution at the end. So you'll get 3 out of the 4 here. Remember, for this, for the dilution equation, the milliliters versus liters doesn't matter. Molarity has to be in liters, but dilution, if you start in milliliters, you end in milliliters, and that's fine. You don't have to convert it to liters. Molarity, again, here we have moles and liters. So since molarity equals moles per liter, I've got the two numbers to plug in, 1.457 moles, 1.500 liters. I just have to do the math here, and I get 0.97 molar solution. I just did 1.457 divided by 1.5. Here's a dilution equation again, M1V1. See, this one is in liters. That's okay. If you start in liters, you end up in liters. If you start in milliliters, you end up in milliliters. Doesn't matter when you're doing dilutions. So we have 0.3556 molar solution, and we have 0.1718 liters of it, and we dilute it to a concentration of 0.122 moles. The question is, what is the final volume? So I didn't mention this in the first one, but remember, I like to look at these and say, okay, what happened? And what should that do to the other variable? In this case, the concentration went from 0.35, basically 0.36, down to 0.12. So the concentration went down. Whatever you do to the first variable, the opposite has to happen to the second. So since the concentration went down, that means the volume should have gone up, or has to have gone up. So when I do this out, my volume needs to be bigger than that number that I started with. And if it is, that suggests that I did it right. If it went in the wrong direction, that tells me I did something wrong. I multiplied when I should have divided, or vice versa. When I do all this out, I find that the volume, so I multiply the left side together, divide it by 0.1222, and I get 0.4999 liters. I started at 0.17, I ended up at almost 0.5, so the volume went up, which is what I expected based on the fact that the concentration went down. So the concentration went down, the volume went up. That suggests that I set it up right and did the math. Okay. And then finally, just be able to be familiar with the different parts of conducting a lab. How do you write a procedure? How do you create a data table to gather data based on a procedure? So if I write a procedure and say you're going to do these steps, what information would you need to collect from that? The mass, the volume, and so on. And how would you set up a table correctly to do that? How, if I gave you some data and said calculate, for example, density or concentration or something with dilution, you need to be able to perform those calculations. If I gave you a bunch of data and a hypothesis or a purpose statement, could you write a short conclusion saying, here's what the question was, here's what the data shows, here's our conclusion. So be able to do those things, be familiar with them, go back and look at the lab report template that we used. That will give you some insight as to what should be in a procedure, what should be in a data table, and so on. So there'll be a question, there should be a question like that. Right, I'm going to give you a periodic table. I will give you a reference sheet that has it actually has the molarity and the dilution formulas on it. Percentage calculations, you need to remember that it's the part divided by the whole. And I'll provide calculators if you need them, but if you have a calculator, please bring it, not your phone, an actual separate calculator. All right, there you go.